Well, good morning, everyone, and welcome back. My name is Gloria Mico. I'm a PhD student here at the Photonic Research Labs, and I hope you are all wide awake and full of energy to enjoy the next session about hybrid photonic integration. So the first presentation of this session will be given by Kristinn Gylfason. I'm sorry if the pronunciation is not the best one, who leads the research on optical biosensor and photonic micro and nanosystem at KTH in Stockholm, Sweden. And today he's going to talk about silicon photonic MEMS for reconfigurable PICs. Kristinn, wherever you want.
Thank you. All right. Thanks for the introduction, and kind thanks for the organizers for inviting me here to Valencia. I've had the pleasure to have many good collaborations in Valencia, and it's always a pleasure to be back. Also, I want to thank them for the perfect program organization, because now I can basically just summarize my talk today in one sentence. So we are actually here trying to implement a new hardware solution for the kind of applications that were presented by the two keynote speakers yesterday. So it will make my life very easy on the presentation, on the motivation part today. So the new work I'll be showing you today is part of a European project called Morphic, and it's six partners in Europe. It's coordinated by IMEC in Belgium, in Ghent and Leuven. They do the silicon photonic processing and also some design. And then there are two groups that work on MEMS. It's EPFL and my group at KTH. And then we have Tyndall Institute in Cork that do photonic packaging and electronic controls. And then we have the local group here in Valencia, VLC Photonics, that are designing designing circuits for one of the demonstrators and also doing the evaluation. And Comscope in Belgium also has one of the demonstrators. So I just want to acknowledge a few people. Of course, it's a big effort, but there's lots of people involved. But I just want to acknowledge a few people here. First of all, Wim Bogaerts, the coordinator of the project. So this whole thing is actually his brainchild. And if you know Wim, you know he's really involved in all the details of the project, solving all the difficult problems. Then the team at EPFL is Professor Niels Kwak and his two students, Yuji and Hamed. That work very closely together with us on the MEMS. And the team in EPFL has developed the post-processing I will show you today. And then I just want to acknowledge my two students, Carlos and Pierre. So Carlos is actually from Valencia also, so that's a nice connection. And yeah, it was basically me and Carlos who started working on this photonic MEMS in KTH in 2013 together, so that has grown quite a lot in the recent times. All right, so I don't think I have to introduce so much to you the concept of a photonic integrated circuit, but basically the idea is to put all the photonic functions you want to have on a single chip in a kind of parallel way to electronic integrated circuits. And today, as was very well explained yesterday in the keynote talks, all photonic chips are application specific. They are designed for one purpose. So let's say you have a transceiver chip that works with a certain modulation technique. Then if you want to change it, you basically have to design a new chip and fabricate, test, and then if you want to go make another change, you want to go to wavelength division multiplexing, that's another round. Redesign, fabricate, test. And then, yeah, you would have to have 3 chips. And this is very different from how electronics are made today, where we have readily available field programmable gate arrays, where such a trial and error or let's say prototyping round can be done much faster. So in electronics, you basically pick a existing FPGA or DSP, then you program it and test it. You can verify your idea, and only then if you see, okay, I need to go to very large volumes and I need the maximum performance, then you would design ASIC and order from foundry. So today there is no equivalent thing in photonics. So this is where we are working. So people call these things different names: programmable photonics, photonic processors, universal photonic circuits, but they are more or less the same thing. So we are talking about a photonic integrated circuit that can be reconfigured using software only to perform different optical functions. There has been some work in this direction. I just want to mention a few things. So here was a 6x6 T matrix implemented in a low index contrast medium by a group in Bristol in 2015. Here's one silicon by the WIMS group in Ghent. It's a 4x4 circuit. And these are implemented using integrated heaters for the tuning. So the end goal is actually to create something like this. We couldn't call it a generic programmable optical processor. So ideally then we would want to take advantage of the PIC technology and put on the same chip high-speed modulators, photodetectors, maybe some application-specific circuits, and then we would connect all these different parts using a generic programmable optical mesh network. And as Jose explained yesterday, ideally this network should allow both forward and feedback operation of the optical signals. So yeah, there's been lots of theoretical analysis of this kind of networks, and it can be shown that you can implement such a network with just 2 fundamental components: phase shifters and couplers. There are a few different versions. Essentially, only one of them needs to be tunable, but what we in the project, we look at tunable versions of both of them, basically. So if you have those, you can make some very nice things. So you can, for example, on the fly, route light in your mesh, send it to different directions, and reconfigure it. You can split light to different outputs. You can recombine it again and keep everything in phase using the phase shifters. Or then you can start to really play around, make some filters, Mach Zehnder, or even do a loopback interference filter like a ring. So then if you would have that, instead of having to redesign and refabricate your chip, you would just reconfigure your mesh, basically, and can achieve the different functions you want. So that's the dream. There has been some progress, and here's a very important one that Jose showed also yesterday. So this is a 7-core hexagonal mesh implemented with heaters by his group here in Valencia. But if we really want to get where we want to go, we need to scale this up a lot, actually. We probably need tens, hundreds, or even thousands of these cores. So how do we do that? So to scale this up, we need very, very good building blocks. They should be compact, take small space on the chip. They should have short optical length, because otherwise they limit the kind of interference cavities you can create. They should have very low optical loss, otherwise you don't get out any light in the end of your mesh. And they should consume very little optical power, because optics is very temperature sensitive, and if you're heating everything up, it's very difficult to control. And then we need many of these. So we have to have a technology that allows us to really make lots, thousands. And when you make thousands, you need to monitor them also to verify that the network is actually doing what you want it to do. And you have to control all these things. So in the Morphic project, we're working more or less all of these aspects, but I will only talk about these actuators today. This is what I do. So what are the options actually to achieve this kind of functionality in photonics? So this kind of qualitative picture is from a recent review we published in JSTQE, where we're analyzing this situation. So the current technology that is most popular for these kind of things are thermo-optic active components. They are very mature technology. They're readily available in the different foundry processes, but they consume very much power. And what we sort of argue in the paper is that there are really three factors that are most important for scaling. It's the power consumption. Three factors. We kind of map them on 2 dimensions in this plot to be able to visualize it. So it's the optical power consumption per component. It's the loss per component and the footprint per component. If you map it out like that, you can see that there is a technology called MEMS that actually is quite a nice trade-off between those aspects. So that's why we are working here. So mechanical, when I say mechanical tuning, people think, oh my God, this is going to be very slow. But we are not talking about, your benchtop mechanics. We are talking about micro and nano mechanics. And if you look at the speed you can achieve with this kind of things, they are actually faster than you might think, because they have a very small mass. So you can move them around pretty fast. So, up to a gigahertz mechanical resonators have been shown. So, but microseconds is definitely possible with MEMS technology. And one other thing that stands out is that you get very strong changes when you actually move things around. So you can have very dramatic tuning. And that allows you to make things very compact. So that's very different from, for example, things based on Chi2 nonlinearity. They are super fast, but typically you need very long devices to achieve appreciable effects. Okay. So how do we do this now with the mechanics? So we work on photonic integrated circuits. So our light is propagating in waveguides. So we have a waveguide core, and there's a guided mode. So if we want to, we can basically do this in 2 ways. If we do it in a single layer, then everything has to be in one plane. Then we have the waveguide core and the signal, or the mode propagating on it. And then we have a slab of material that we can move around. So we can do it in the plane, or we can do it out of plane. Or if we have 2 layers, we can move it like that. So, and then a coupler, there it's 2 waveguides. Or you move it out of plane. Same thing, if you have 2 layers, you can make two waveguides on top of each other. So that's basically the whole toolbox. And we have come from the MEMS field, and in there, there are very mature technologies to achieve displacement on the very small scale that we need. Sorry. So we have these electrostatic comb drive actuators. Sorry, I have a bit of a cold. And with those, we can achieve a submicrometric displacement on chip using just voltages of around 10 to 30 volts or so. And this, can all be put in the same layer. So, and then if we combine all these things with the silicon photonics foundry process that's readily available, we can achieve complex functionality in a compact chip at low cost and in a platform that can be scaled to high volumes. And since we do work in silicon, we get all the benefits of the silicon material itself, which has really driven the success of MEMS technology. So silicon is very nicely elastic, and these electrostatic actuators are very low power. So for example, you have these accelerometers from Bosch. The whole thing is, including electronics and everything, draws about 240 microwatts. So you can put it in a clock like that, and it will run 1 year on a battery. So this is really what we take together to do what we are calling silicon photonic MEMS. So this concept has been around for a while, and I just want to mention a few pioneering groups. With a few different approaches, like I said, you can work in two layers. And that's really the group of Min Wu in Berkeley. They have done lots of very nice two-layer systems. Or you can try to put everything in single layer. It's really, I think, the approach to use if you're going to work with a foundry fabrication process like we do. So that's something we did a few years ago. But also I want to mention the group of Professor Harner at Tohoku University. They really pioneered this field. There's some very nice early demonstrators. So here's one thing we did a couple of years ago. So it's a tunable tunable ring resonator based on MEMS. So it's a small part of the ring actually is also doubles as a cantilever. Then there's a static rim out here, and we can pull this part up or down. So then the waveguide is actually moving in this case. Sorry. And the static rim is over here. You pull it up and down past this rim. You change the overlap of the evanescent field with this little part here, and then you can tune the effective index of the guided mode in a curve like that when you kind of pull it through the central plane. And we kind of use the fact that these things are typically buckling out a little bit because of stress when we release them. So we can really get this full actuation curve. So that's how the thing looks when you fabricate it. And when we test it, we see it works pretty nice. And it's, as I mentioned before, it's quite a powerful tuning. So we can tune by 62 picometers per volt, or equivalently 7.6 gigahertz per volt. And you really recognize the shape of the tuning curve there in the result. So then in the Morphic project, we are really now trying to scale this up. So we're implementing this silicon photonic MEMS technology in a real silicon photonics foundry platform. And so we're using the IMEC ISIP 50G platform, which has all the nice optoelectronics, the high-speed modulators and phase shifters. And we add this very low power and compact silicon photonic MEMS. So The only thing we do is a few post-processing steps. So we open up and under edge the movable parts, and then we actually also seal the thing again with a cap, something we do at KGH. So we just got back some chips from the foundry just before Christmas. So here are some nice pictures. That's it's a crossbar array. Ah, thank you. And here are some phase shifter concepts. And just so that you believe me that this is actually suspended, here's a SEM zoom in showing the nice lithography of the IC50G process. So as I mentioned before, we just got the chips back, so we haven't been able to measure too much, but we managed to characterize one phase shifter. So this particular device is in one layer, and it's a kind of a pull-away actuator. So in the in the relaxed state, this small beam here is actually overlapping with the evanescent field. But then when we actuate, we pull it out, so we move this beam away. And that's a top view of the thing. And actually, it performs very well. So here are about 3 different variants on the chip. So they differ by the size of the waveguide core, the width of it, and also by the initial separation of the 2 beams, or the little tuning cantilever. So you see if they're very close together initially and the core is very small, you get very strong effect. So we can get over 2 pi phase shift in 35 volts. But when you have such a dramatic tuning, you have quite a big loss, and the loss is also actuation dependent, which is not ideal if you're going to use it in a mesh. On the other extreme, if you have the wider core and bigger separation in the beginning, the tuning effect is smaller, and we achieve less than half a pi before it kind of saturates. So the ideal point is somewhere in the middle, where you can achieve a 1 pi phase shift with very, very little insertion loss in this device. And it also doesn't vary a lot with actuation. So we are quite happy with this result. And if we look at what people have been showing before, so that's a plot from our review paper, which is listing all the published MEMS phase shifters in the literature. And we characterize them using what we think are the two most important characteristics of these kinds of things. It's basically the length of phase shifter required to achieve 1 pi phase shift versus the insertion loss of that same length of phase shifter. Then the performance of these devices basically increases down to the left corner of this plot. And the one I'm showing you actually is kind of, let's say, state of the art already. And just have to point out that all the other points here are basically discrete devices made by E-beam or so. So this is really the first one that is actually made in a real foundry, available foundry process. All right, so that was about what I wanted to tell you about. So I think I've hopefully convinced you that silicon photonics with integrated MEMS is a very promising platform for scaling up optical meshes. And we have demonstrated that we can integrate photonic MEMS actuators monolithically in the ISAP 50G foundry platform. And I've shown you some very early results showing promising performance. And it's going to be a very exciting time now, the next couple of months, when we continue to evaluate all the other stuff that is on these chips. All right, so I would be happy to take any questions that you have. Thank you.
Thank you, Kristinn. So,
two questions.
Yep.
In the end, for these devices to operate well, I think you have to tune say the couplers and so on to less than 1% accuracy.
Mm-hmm.
So what is the stability of setting the phase to a certain value over time? And would you also be interested to reduce the voltage in order to drive these devices to be more CMOS compatible?
Yeah, so two good questions. So yeah, we haven't studied, long-term stability yet. So these are rather recent results. But I think we can rely a lot on the experience of the MEMS field in that sense. So there's a lot of knowledge about long-term stability of accelerometers and gyros and so on. The nice thing about silicon, it's perfectly elastic. So you can push it back and forth millions of times, and it will do exactly the same thing every time. So if you design your components in such a way that you have just elastic transformations, there's no contact here. That's important. Then we believe the stability can be very good. Then it's essentially limited by your electronics, let's say. Temperature is important also. Of course, this is silicon photonics. So thermo-optic effects are difficult. And that's why we don't believe in thermal tuning, because crosstalk is just going to be terrible with that technology. This is going to be much better here. So I didn't really mention it, but the power consumption of these things is negligible. We cannot really measure it, actually. So it's very small. And it's below, it's in the nanowatt range, at least, we would can be sure. The other question was about, sorry, what was the second one?
Voltage.
To reduce the voltage, okay, yeah. So that's a design parameter. So we can reduce the voltage, but then we have to make our actuators softer. And that makes them more susceptible to variations, and they would also be slower. So we can choose to make them softer, but I think right now this is fine because we have access to electronics that can actually do 50 volts. So that's standard components by now. So that's not a limitation here, I would say. Oh.
Thanks.
one more question.
Good morning. Thank you very much for the talk. I have a question. What is the range, the length range of your phase shifters? The current one, yeah.
How long we make them?
Yeah.
We typically try to make them as short as possible. So this one here is about 50 micrometers. I think we have shorter and longer ones. I don't remember exactly, but it's that kind of size. Okay. And this is giving us 1 pi in 50 micrometers.
Thank you.
Yeah.
Okay, last question.
So you showed in the beginning of your presentation a very nice, just a little bit forward, a very nice accelerometer. So don't you have the same kinds of issues with these kinds of circuits that they will also act as accelerometers, so that they might be sensitive to mechanical influences from the outside?
Yeah, good question. So even though this is same technology as MEMS, it's a totally different time scale. So MEMS gyroscopes and accelerometers and so on, they are tens and hundreds of micrometer size. So there's much more inertia. It's like a totally different scale. So we are making mechanics in the 220 nanometer thin silicon device layer. So these devices have extremely little inertia. So yes, sure, if you put them in a shaker and vibrate forcefully, they would probably measure acceleration, but I don't see that being a problem in a typical application of these things. So they have resonance frequencies probably in the hundreds of kilohertz range, actually.
Okay, and one last question. How quickly can you switch these kinds of MEMS objects between different states? It's
a linked question. So I was kind of promising you in this plot here something like microsecond switching times, and like these we haven't really pushed yet, and basically it's going to be limited to if you have them packaged in a vacuum or not. Because air damping, if they are in atmospheric pressure, air damping is the dominant mechanical damping here. So that's why we're actually working on vacuum packaging in the project. And if you have that, just based on literature, you can get up to these microsecond switching times.
Thank you very much.
So thank you very much, Kim. We need to move on to the next speaker.
Thank you.